hardware-accelerated AI Web Application Firewall, which is a project that we've been doing for the past few months, and we're very excited to show it to you. So, first I'm gonna shortly talk about the agenda of the presentation. So first we're gonna tell you about the evolution into hardware accelerators. It's like a little bit of the history of like how it was shaping up. Then we're going to present the problem that we were actually trying to solve. And then we are going to present a few solutions, some legacy approaches, and then finally the modern approach that we came up with, along with some implementation details. Then we're going to talk a little bit about future vision. So like what other applications can we have for this technology that we were working with, and a summary, and then the questions that were most frequently asked by people that we showed the presentation to. We just want to quickly answer them. So let's talk about the CPU, the computer architecture, and how it has been evolving beyond the CPU-centric approach. So a long time ago, computers were a box with a bunch of lights on it, and you turn on one lights, and then you saw the output on the other lights, and there was no input-output, and it was like a research thing. But then, to do anything that has some kind of usable quality to it, you need some peripherals, right? So a disk or a NIC. So what we did is we came up with a PCI architecture, and we connected all the peripherals that needed to interact with the outside world to the PCI bus. But all the peripherals were very simple. They were designed to do one thing, and they were doing it very well. So the disk was saving the data, the NIC was interacting with the internet, but there was no computational capabilities on the peripherals themselves. All the operations were managed by the CPU, and the peripheral was only like taking the request, processing it, like doing something, and then returning the data back to the CPU. And all the computations were present on the CPU. Then we moved on to the central architecture with acceleration, right? So we came up with dedicated hardware accelerators that were designed to make some computations faster. Examples of that could include cryptography, so encryption, decryption. That is something computationally intensive. That's it makes sense to like offload it to a separate device that's going to make it faster. And regex accelerators, which was interesting to me. That's apparently something that happens. That is a strong use case with HTTP traffic, with HTTP servers. Obviously, there's a GPU for graphics processing, and SmartNICs. And with SmartNICs, it made sense to accelerate the computations on the device itself, because the data that comes in could be very quickly altered or worked with close to the data itself. So we could do NAT, we could do some Ethernet manipulation, or maybe custom protocols, or encapsulation or decapsulation, very close to the data, like strictly where the data appears. Or just block or approve some traffic. So that made sense to have computational, like some basic computational capabilities also on the SmartNIC itself. And then these computational capabilities worked very, very much like the previous case, right? So like there's a request sent by the CPU to the accelerator versus to the GPU, right? To like draw a frame, and then the GPU just draws the frame, and then the data is output to the screen. So while the peripherals had computational capabilities of their own, they weren't really able to manage that and communicate within themselves. So that's what happened later, where right, previously we had like so for instance, to process some data from the NIC on the GPU, you have to like take the data from the NIC, then move it to the CPU, then from the CPU to the GPU, then back to the CPU. And then, for instance, if we want to input a flow to the card so that the next packets that are the same would be processed in a specific way directly on the SmartNIC, we have to do yet another transfer to the NIC, right? So we have four transfers. And now we're approaching decentralized architecture where peripherals not only have computational capabilities of their own, but they also can send the data directly between themselves to accelerate this workflow even more using peer-to-peer DMA on the PCI architecture, right? So for the use case that I talked before, the data appears on the SmartNIC, and let's say that we want to input some data to the NIC depending on the GPU calculation, then we just do 2 transfers instead of 4. One transfer is to the GPU, then the GPU makes a calculation, and then the result is sent back to the SmartNIC. And the same idea could be used for Smart Disk or any other accelerator that has this capability, and that frees the CPU to do other tasks in the same time. So now I'm going to shortly talk about the problem that we were solving. So the web application firewall, a very simple use case, very common. We have some clients that are trying to get to an HTTP web server, and the web servers are vulnerable. It just happens. So and the clients sometimes have bad intentions and want to hack the server. So the idea is to just classify the requests between the good ones and the bad ones, and allow the good ones to go through, and the bad ones need to be blocked, right? So like a very simple firewall solution. Now I'm going to talk about the legacy approaches, so how this used to be solved before. So the simplest stuff is a CPU-based solution, right? We have a NIC, we have a CPU, and the traffic comes in on the NIC, and the unfiltered traffic goes onto a separate application on the CPU, that is the firewall. And then the traffic from the firewall, if deemed not malicious, it's then forwarded to the HTTP server. The pros of that is that it's obviously very simple to implement. There's no additional hardware or software complexity. And we also don't have to spend money on the hardware. However, this has some performance implications because we cannot just use all the CPU power for just the HTTP server. And the HTTP server is going to take all the power you're going to give it, right? Because like if you don't run one instance, you're going to run multiple instances, and there's always going to be more traffic to handle, right? So like you need as many cycles as possible for the HTTP server, but you have to like divide that between that and the firewall. The firewall also is going to be rather simple, right? The apps that are are written on the CPU are usually relying on a set of heuristics, right? So like, you know, if it kind of looks like it's bad, it's probably bad, you know, and it's basically just a bunch of ifs that filter out the most common cases, which isn't very extensible, because to extend that, you just have to add more ifs. And also the firewall is not isolated from the HTTP server. So they're both here on the CPU. So if you manage to compromise the firewall, right? If you manage to successfully attack the firewall application, you're not only going to get data from the firewall application, but you're also going to get the score, the most important data that resides on the HTTP server. So let's talk with machine learning with a GPU-based solution. So basically, let's add a GPU to it, right? So now the traffic comes in from the NIC, then goes to a special app that is just a packet handler, and that packet handler forwards the data, like a subset of the request, to an ML model that is present in the GPU, and then the AI determines whether the request is malicious or benign, gives the result back to the packet handler, and then if the result was benign, it's forwarded to the HTTP server. Now, this significantly improves security because we have a smarter classifier. We haven't really found a limit to what the AI can do yet. Literally, like a few days before recording this, a new model was released, the DeepSeek, right? And then it's even smarter, even than the OpenAI ones, right? So it's even better now. And in a week or in a month, somebody's gonna release an even better one, right? So this is still growing, and it's definitely much better than a bunch of ifs. And the CPU is also not used for classification, so we free up the CPU power to handle what is important, which is the HTTP traffic. Now the cons, unfortunately, we need to buy the GPU, so that's obviously hardware cost and software cost as well, because we need to integrate that also and write this whole packet handler and all this code that's going to run everywhere to handle that. It also requires a well-trained firewall model. However, these things are available on Hugging Face and open source solutions. Obviously, if they're available on open source solutions, hackers are already going to know how to circumvent that. But it is a very good starting point. So it's not like you just have to always make your own model. There are good starting points for that as well. And what's also interesting, and the firewall packet handler is still not isolated from the HTTP server. So if you manage to compromise the packet handler app, you're also going to get all the data from HTTP server as well. And now to talk about the modern approach, I pass the microphone to my colleague, Michał.
Thanks. Okay, so the approaches that Marcin talked about, they were CPU-centric, meaning that the packets were still managed by the CPU that were processed by the firewall. In our modern approach, we implement the decentralized model where the packets are entirely computed, entirely processed outside the CPU, leaving the CPU entirely for HTTP server. To accomplish that, we have used SmartNIC, specifically NVIDIA Bluefield DPU. DPU is a network interface card that has also some ARM cores that allow us to run basically any code on it. For example, we can even run an entire operating system directly on the network interface card. But what's most important is that we can run network management code on this DPU. So the packets that come to the card, in many cases, they even don't need to leave the card to be processed. Additionally, DPU comes with some acceleration engines that, for example, allow us to insert some rules that can match some packets, and we can assign actions to those rules. For example, packet forwarding, modification, or blocking. This allows us to process the packets that match those rules even faster than compared to the packets processed by the ARM cores. So moving on to our web application firewall. So how have we used the DPU? So first we replaced the regular NIC with DPU, and thanks to that, and thanks to those ARM cores that come with the DPU, we're able to move the CPU firewall packet handler to DPU. Thanks to that, the CPU is now is not used for firewall at all after the initialization part, which still requires CPU, but for data plane it's not used. And everything is running on this DPU and the GPU. This isolation allows us to increase the security of the solution, because we don't have this problem where the firewall packet handler has some issues that can be like utilized to steal some data from HTTP server. I mean, it's much harder because now if something happens, then we also need to somehow get those data through from this from CPU to DPU. So it's much harder. Additionally, DPU allows us to perform some packet preprocessing. In our case, it was HTTP header extraction. So basically, the firewall model that we're using doesn't need to process the whole packet. It only needs like the HTTP header. So instead of like sending the whole packet, we are able to extract this and the HTTP header and copy only that. This can save some bandwidth and improve the performance of the whole solution. Additionally, DPU allows us to insert some rules directly at the at the entrance, let's say, to the DPU. For example, when we recognize an attack, instead of blocking only the single packet, we can block entire user that caused this attack. Yeah, and of course there are some disadvantages of using DPU. First of all, we need to buy this, and DPUs are not cheap hardware. Especially they're more expensive than regular NIC, that's for sure. And the other thing is that the whole solution is harder to integrate, because the DPU is a new technology, a new device. So if you want to do something that is not well documented, then it's obvious that you get some issues that are hard to solve. But yeah, we managed this, but there were some issues in the process. Okay, so now I want to summarize our solution with some sample packet flow. So let's say a packet arrives to the DPU, and this packet is copied to firewall packet handler. The packet handler extracts the HTTP header and writes the data to GPU memory via DMA. Next, the web application firewall model takes this data and performs the classification. Next, the firewall packet handler reads the result from the web application firewall model and performs the action. So either the packet is dropped or forwarded to the HTTP server. Okay, so in order to eliminate the CPU usage from the packet processing of the firewall in the firewall, we had to use some interesting technologies. And now in this part of the presentation, I want to take a closer look at some of those some of parts of our solution. So first of all, I want to talk about how we managed to directly copy data between DPU and GPU without the CPU memory in between. So to accomplish that, we have used peer-to-peer DMA. So peer-to-peer DMA is a way to transmit data between two different PCI Express devices without the use of CPU. So, in our case, where we had DPU and the GPU from NVIDIA, we were able to utilize NVIDIA GPU Director DMA technology that allows us to expose GPU memory in the physical address range, and then the other devices can take this address range and map it in their DMA engines. So those devices can write to this memory like to any other, for example, to other CPU memory. It doesn't matter from the third-party device perspective. The next thing I want to talk about are how we manage to run the web application firewall model without the CPU involvement, because typically it look like this. The firewall, we receive a new packet, and then the CPU starts the firewall model that classifies this packet. But we managed to do it entirely on the GPU, so the CPU is not involved in any part of the firewall packet handling. So to accomplish that, we used CUDA graphs, and a few words about them. So CUDA graphs allow us to define the execution of the sequence of operations on GPU in a single optimized structure. This graph representation is used to define the dependencies between different operations. So, for example, if you take a look at the picture, then nodes are the operations that we want to execute on GPU, and edges are the dependencies between subsequent operations. Storing the whole solution in storing the operations, the sequence of operations in a single structure allows us to reduce the CPU overhead. Because if you want to execute some set of operations multiple times, but for example on different input data, then instead of recreating this graph of dependencies every time you want to calculate this operation, you just need to create this once and then restart the whole CUDA graph. So the CPU doesn't need to recalculate all this thing again and again. Another thing is that CUDA graphs improve is that if you have multiple operations that are independent on each other, and you can execute them in parallel. And if you take a look at the graph, then it's easy to determine whether the operations are independent or not. Because, for example, if you take a look at B and X, then there is no edge between them. So theoretically, if you execute A, then B and X can be later executed in parallel. So how have we used the CUDA graphs in our web application firewall? So the solution was split into three parts. First, we had the init kernel, which basically waits for data to appear for machine learning model. It waits for the DPU to write the data into the GPU memory, and also set some flag that the data is there, so that the init kernel can read this flag and proceed to the next step. Next, we have a machine learning model, which is actually a captured PyTorch model, because PyTorch actually uses CUDA graphs underneath. So it was quite easy to integrate. The ML model performed the classification, and later we were executing the post-execution kernel, which takes the result from the machine learning model and makes it available to the user, and also signals the DPU via this flag I mentioned earlier that the data is ready to be read. Post-execution kernel has also one other important role, which is tail launching the whole solution again. So as I said, typical solution would be to start this CUDA graph once, and then CPU would need to like restart the whole solution again and again for each packet. But tail launch allows us to schedule this whole graph directly from the GPU, so the CPU is not involved in restarting our solution. Okay, and now I will let Marcin to summarize our solution and present the vision for the future.
All right, so let's talk about the summary. Let's start with the vision for the future first. So we have some cool technology that we worked with here that allows us to basically connect two peripherals that have computational capabilities without CPU involvement. So and we did this between the SmartNIC and the GPU. But what other use cases could be used here? So for instance, if we connect a smart disk to a SmartNIC, we could have various solutions like CDNs or DBMSs, so content delivery systems or database management systems. I've actually seen this kind of solution being utilized by the Korean Institute of Technology. They had a showcase on a conference that did exactly that. And I think there were some kind of talks that like huge streaming services are going to be exploring this direction to accelerate reading the data from the disk and putting them directly into the SmartNIC. And if the disks are smarter, we could also implement some kind of database management system. So we could have like some more features like duplication and maybe a distributed system, right? So within one computer, multiple disks or multiple disks between multiple computers, if the disks allow for that. And then also like I imagine that this could also all work without CPU involvement, just between disks synchronizing between each other. So that could be faster. Another idea, if we take the data from the SmartNIC and then put it directly in the smart disk, would be maybe a monitoring or a data gathering solution where we take the data that appears on the NIC, and then maybe we mirror this for later inspection, or we do some pre-processing instantly. As Michał have said, the DPU has some pretty powerful computational capabilities of its own. So maybe this computation could also run on the DPU itself, and then we could just like save the results to the smart disk. And then all of this could like work completely transparently for the CPU, and then we could inspect the disk results for later conclusions. What we could also do is caching intermittent or final results of machine learning, right? So let's say that we have a machine learning case or an AI case where the input is small, but the output is very large. Like for instance, generative AI that is prompted to make a video of Abraham Lincoln singing "Happy Birthday," right? So like the prompt is very short, Abraham Lincoln singing "Happy Birthday," but then it probably for today's models it's probably going to run for like a minute or a significant amount of time, and then produce a result that is also sizable. It's a video, so it would make sense probably to if another request like that is made to the ML, we could just cache that, right, and then ask the disk. In the meantime, like, do we have this kind of result? And then be very efficient in producing Abraham Lincoln's singing "Happy Birthday." All right, to sum up the whole presentation, the computer architecture has been decentralized. It used to be just a CPU with peripherals that were just doing one task. Now, a lot of the peripherals have their own computational capabilities, so it makes sense to write code for these capabilities and connect them in new ways so that we can leverage this architecture to to accelerate, for instance, a deep packet inspection application running on a GPU instead of a CPU that we used to do before. The data is sent directly between the DPU and GPU using peer-to-peer DMA. We could also use the same kind of technology to transfer the data directly between other peripherals as well, without CPU involvement, as long as the computational capabilities are there, and it's fast, and not only it's not only this could be faster than it was before because of avoiding additional transfers, but also it frees up the CPU to do other stuff at this time. So it's there's definitely potential for efficiency. All right, now we're going to quickly talk about the most frequently asked questions that were asked to the presentation when we were showing the presentation to our colleagues. So the first question is, did CodiLime create and train the ML model for the firewall, or did you use a publicly available open source model? So we actually took a publicly available open source model. There were many components to the project, so we were really just trying to make it work and not really spend any more time on like a specific part that we knew could be improved later. Besides, ML is like a thing in of itself, and making a reasonable prediction model for this case could be like an entire project in of itself, right? That that could take months. So we decided to use a publicly available open source model. Michał, maybe you can answer the second question.
Okay. So the second question is, why did you use a separate DPU and GPU instead of a DPU with an integrated GPU? So there are actually two reasons for that. So first of all, the financial reason. Basically, DPU with integrated GPU is much more expensive compared to the separate DPU and GPU. The other reason for this is that having this separation allows us for more flexibility. We can, for example, easily replace the GPU or even add more GPUs. And in our case, with our solution, the changes in the code would be minimal. But in the case of DPU with integrated GPU, it's impossible to do it actually. So yeah, but obviously that if you have like a single DPU with integrated GPU, then the solution would be faster, because we don't need to even copy the packet outside the DPU. It's everything like in one place. But our solution, in our case, we wanted to do something different, and that's what we did. And the third question, I'll let Marcin answer.
All right. So what was the effort needed to implement the solution? The effort was actually sizable, and there were like multiple parts to this, because if you think about it, there are like three components that we need to cover. So there is the CPU that has the initialization part and the configuration part. There is the DPU part that has all the code that is very close to the data on the NIC. And then there is the GPU part that handles the ML and everything. So what we did is we wrote the initialization app. So all the research with peer-to-peer DMA and configuring the MMU and making sure to connect all of these parts in such a way that would enable this to work. Then there was the DPU code base that we had to we used a proprietary SDK called Doka, right, for just manipulating and working with this with the DPU, and then extracting the data and sending it to the GPU. And then there was the whole GPU part. So that was writing the kernels that Michał talked about before. but also working with the model, right? Because if you take the model, it's if you take a PyTorch model, you can't just like dump it on the GPU and call it a day. But we had to first migrate it to TorchScript, and then from TorchScript make it a CUDA graph. And then we actually had to hack PyTorch itself a little bit. Not too much, but we had to expose like internal pointers, internal GPU pointers of PyTorch, so that we could use them in our code, so that we could avoid copying data, and the data that's being DMA'd onto the GPU lands directly where it's necessary. So it was complex. It was very interesting. It was one of the coolest projects that I've done at CodiLime. It was great to work at it. But yeah, it was definitely a lot of different parts. Thanks everyone for listening to our presentation. My name is Marcin Parafiniuk, and it was nice to talk to you.
Yeah, I'm Michał Niciejewski, and thanks for listening for this.
Oh yeah, there's also a research paper that we did with all of our conclusions that is going to be available in the resources section. So I invite you to check that out as well. Thanks.
Thanks. Bye.